Hello everyone, welcome to my channel. So in previous video we have discussed about constraints of embedded device and different data types that can be used for programming the embedded device for efficient execution of the code. In this video we will be interfacing an LED with a simple switch to an STM32 microcontroller. For that purpose our target microcontroller in this video will be STM32 F401 RET. So from now on, any code that we develop will be for this target microcontroller only. Without any further delay, let's move to the next section. So for today's video, we are defining few objectives. Before moving into objectives, I recommend to pause here and think what might be the steps that we need to do to toggle an LED based on a switch input. So simply if you think of it, you have to read the status of the switch, and then if it is like this, if the switch is turned on, you turn on the LED, or if the switch is turned off, you turn off the LED. So the objectives are also same way. Read the status of the switch. If the switch is on, turn on the LED. If the switch is off, turn off the LED. So these will be the objectives for programming our target device today. And coming into the next section, steps of programming for STM32. If anyone are following the series from the beginning, in the first video I have mentioned we have to enable clock for GPIOs when we are using them. So for that purpose, there is a register I have used in the first video, RCC arrow AHB1 ENR. So from where did I get this AHB1? If you closely observe the reference manual, we have many other registers like APB1 or AHB2. So among these registers, why did I choose AHB1? Is there any book or reference that is speaking about this? Yes, there is something. So the thing which you are seeing here is the internal architecture of a ARM Cortex M4 chip. So if you closely observe, these are nothing but the lines that are coming here are known as clock lines. See here, you can see AHB1 120 megahertz gray color. So if you follow that gray color line, it came here, and the AHB is split into like it is divided as APB2 or APB1, but still it is all coming from AHB1 only. So from AHB1, the clock is being provided to all the timers, USART, I2C, I2C2 and all, and along with that the clock is also being provided to all the GPIOs here. If you can see AHB1 120 megahertz, the clock is being provided to all the GPIO ports here. So from this, what can you infer is, if you want to enable clock for GPIOs, you have to enable this AHB1 advanced high speed bus. So the first thing is enable clock for necessary ports, and once you enable clock, resetting GPIOs is a main and important step, because if you reset the GPIOs, that means they are ready to use either as an input or as an output. So resetting a GPIO means configuring the GPIO mode as 00 in the moder register, or simply to say you are making the pin high for it to readily accept the input, and configuring the GPIOs for input or output. Once you reset the moder register of that particular GPIO pin to 00, then you can configure the GPIO for input or output. Let's say for if you want to configure it as output, then you will make a OR with 01, or if you want to configure it as input, you will keep it in the reset state itself. And then comes the PUPDR register. So like you might have doubt ki why PUPDR, that will be discussing in the next section. So PUPDR is nothing but pull up pull down resistor register for necessary pins. What are these necessary pins? So if you are configuring any GPIO as an input, it is mandatory that you either pull up the GPIO or pull down the GPIO. Based on your requirement, you need to configure the PUPDR register for that particular pin. And once you are done with these, After resetting the PUPDR register, you have to configure the necessary pins for pull up or pull down with PUPDR register. Once you are done with this, you have to read the necessary IDR. What is IDR? Input data register. You have to read the necessary values of input data register and actuate peripherals by configuring necessary ODRs. ODR stands for output data register. So for example, if you are configuring GPIO A or PA.0, like PA.0, if you are configuring as input, and I want to activate let's say I want to activate PA.4, PA.4 to 1 if PA.0 is 1. So you can simply, what you can do is you can monitor the IDR. So what you will do is GPIO A arrow IDR will directly give you access to the input data register of GPIO A. In this, what you are monitoring? Only the PA.0. PA.0 means you have to directly bitwise and with 0x01. So this will give you the status of the last bit. So if the status of the last bit, like whatever the status, it will return it. So if it is like you can keep it as, let's say, flag. If flag, you can directly write GPIO A arrow ODR, like you can directly write 0x10 or something like that. So this is nothing but reading the IDR values from the necessary peripherals and actuating the peripherals using the ODR. So as I have mentioned earlier, enabling clock. So for this, let us use port A for this purpose, like for reading status of a switch and glowing the LED. Let us use port A. So the thing you are seeing here is, this is the RCC underscore AHB1 ENR register. In this register, we have 4 bits for different ports, A, B, C, D ports. So and also we have GPIO E port. From that, we are enabling only GPIO A. So this we have to configure as RCC arrow EHB1 ENR as 0x00001. Once you are done with it, the second part is resetting the GPIO motor register. So for resetting the GPIO motor register, the first thing you have to do is you will be keeping the motor value as 00. So if you observe in the previous slide, I have directly written here GPIO arrow ODR is equals to 0x10. So now let us see what are the consequences of writing like that, or what is the actual method of writing data into the register. So let's say if I want GPIO A motor as 0x0001, which means PA.0 is output. So now if I want PA.3 also as an output, like if this is written in the first part of the code, and now I want GPIO like PA.3 as output in the like fourth part in the sense I'm mentioning in the C code, like if you have some LCD init functions here, and after that you have keypad init functions, and something after that if you are writing some I2C drivers. So after I2C drivers, if you are using this GPIO motor register, here if you are using like you want PA.3 to be output, so you will in the as per the previous notion, you will be simply writing GPIO A arrow motor as 0x0040. Why? Because if you want GPIO 3 as output, you have to convert this as 10. So which means, so if you convert into hexadecimal, this will sorry, you have to convert this as 01. So if you convert into hexadecimal, this will directly result in 0x40. So like you have to convert it as 0x40. Now if you observe, if you are directly equating as 0x40, you are forcibly making the first pin as input, because 0x40 not only makes the third pin as output, it also forcefully drives the first pin into input state, which is not recommended. So for that, what we will do is we will use some combination known as and equal to not of and assigned with negation of to reset necessary ports. So what does this mean? And we use or assigned with to configure the required mode. What does it mean? So this we will see in the next slide. So here if I want to make PA.0 as output and PA.1 as input. So as per our requirement, let us say for PA.0 you are connecting the LED, and for PA.1 you are connecting the switch. So first you have to do, what you have to do is you have to reset the motor register. Always remember rule of thumb, for programming one pin in the respective GPIO motor register, you will be needing 2 bits. So for example, if I want to reset PA.0 and PA.1, you will need 4 bits. You will need 4 bits of motor register. So for resetting, they must be a 0, right? So what you will do is you will reset only those pins, preserving the rest of them. So for that, what you have to do is, let's say GPIO. Here you can see that here GPIO A arrow motor and assigned with negation of 0x 00000 F. What does it mean? So if you are using negation of, these all will become ones, and the only thing which is actually one will be zeros. So if you make a AND operation with it, like for example, if the existing values were some don't cares, don't cares, don't cares, all are don't cares, and the last 4 bits are, let's say, they are also don't cares. So 3 4 5 6 7 8 9 10 11 12, and these are the last 4 bits, let's say. So if you are making AND with this, as the first 12 bits are ones, the AND operation won't affect any of these bits, and as the last 4 bits are zeros, the AND operation will push these last 4 bits into the 0000 state, which is the reset state that we are desired reset state. So the next part is nothing but uh, yeah. So the next part is configuring the motor register of port A for PA.0 as output and PA.1 as input. So as per the reference manual of STM32F401 RET, 01 for a pin is treated as output, whereas 00 for a pin is treated as input. So according to that, what we'll be doing is, in the previous section we have resetted all the four bits corresponding to 2 pins, right? So you have to refer to the reference manual and find out what must be programmed into these bits for the desired functionality. So if you move go front, here you can see what I want is, let's clear this up. So here you are making port A.0 as input, port A.0 as output, port A.1 as input. So for being port A.0 as output, this must be at 01 state, and port A.1 as input, this must be at 00 state. So these are the 4 bits that needs to be configured in the last 4 bits of GPIO motor register. So what you will do is, in the previous section we have resetted it to 00. Now you will make a bitwise OR with the desired value. So the desired value gets copied into the motor register. So the updated motor register will be 0001. This is what the thing we are desired. See, GPIO A arrow motor will be bitwise ORed with 0x001. Once you are done with programming the desired peripherals to input and output, the next part is configuring the pull up pull down register. If you are following, in the previous section we have PA.0 as output, PA.1 as input. So as per my explanation in the first section, PA.1 will need a pull up or pull down. Let us see why. So why should I use pull up or pull down? Let us say, for example, this is a GPIO pin, and this is a switch or button, and here you have some ground, let us say, and this is the microcontroller unit. If you press this switch, it is obvious that here you will be reading a voltage of 0 volts. But what if I did not press any switch? You heard it right. What if I did not press any switch? Literally this pin will be floating. Floating in the sense, the voltage can be anything, like it can be a noise signal or some random value which is very undesired. So to avoid that, we will be uh, forcing some default states for an input pin, which is through pull up or pull down. So what we will do is, for example, if you want to pull up this pin, let me pull up this pin. So if you want to pull up this pin, you simply add a pull up resistor and keep it to VDD. So now if you click on this or if you press this switch, this will read 0. If you not press this, as this is already pulled up, this will read 1. This is known as pulling up. So what is pulling down means? It is just a opposite of this. In the opposite case, what you will do is, you will connect this to VDD and here you will pull it down to ground. So now when you press this switch, it will read 1. If you are not pressing the switch, it will by default read 0. Here if you observe, I am physically pulling the pin to ground or VDD using some extra peripherals. But don't worry, for STM32 modules with Cortex M4, we have a provision for automatic pull up or pull down that will be done to the microcontroller unit peripheral through a register known as PUPDR, pull up or pull down register. So according to the reference manual, 00 in that particular bits of a pin refers to no pull up or no pull down, and 01 refers to pull up, and 10 refers to pull down, and 11 is a reserved state. So for example, if I want to pull up the GPIO pin, which is PA.1, 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 we are making it as input. So if I want to pull up that, first I have to reset it, meaning you have to program 00 into the PUPDR. So if you go back here, you want to keep 00 in this. According to the way that I have told you, writing into the registers, like using and assigned with, not, along with, or assigned with, you have to use these are the rule of thumb. You have to use only these to configure the registers, because using any other combinations like directly assigning it will always erase the existing configurations, which is not desired for any embedded application. So you will first and assign with this value, so that the respective bits of the pin will be reset, and then you will program it with the necessary value to pull up the pin. Once you are done with it, the next part is monitoring IDR, because in the steps what I have mentioned, we have to enable clock, which we have done already, and after that we have reset the GPIOs and programmed it to the desired values, and after that we also use pull up pull down resistors for our application, uh, for a particular pin as an input. And the next and interesting part is reading data from IDR. So this is the input data register format in STM32F401 RETX microcontroller. So if you observe here, we have a 16-bit register, each bit representing the value of each pin. Out of these pins, you have to select only pin that you are choosing to monitor. In my case, it is IDR1. So in order to monitor that, what I have to do is, as a rule of thumb, whatever the pins you want to monitor, you keep them as 1, and the remaining pins you keep them as 0, and generate a hexadecimal equivalent of this IDR. In my case, it will be 0x02, because only this will be there and remaining all will be zeros. Now what will I do is, I'll do a simple bitwise or bitwise AND with this number with IDR. So now what I will get, if you are doing bitwise and 0010 with the existing data present here, this will only return me the data present in the IDR1, that is PA.1, because 1 and 1 will return the exact value present there. So based on that, I can do my next task. The second part is configuring ODR. So in the previous case, what we have done is, in the previous case, we have taken the value of IDR into flag. So in the second case, while we are actuating peripherals via ODR, we will monitor the flag, and based on the value of flag, we will write data into the ODR. As ours is a PA.0 pin that we are actuating, this will be a simple logic of programming into 1 or programming it as 0. It is a slight mistake. You can keep it as AND here, because when you want to change the state to 0, you have to AND it with 0. When you want to change the state to 1, you have to OR it with 1. So this will be GPIO A arrow ODR and assign with 0x00. Once you are done with this, the next part will be assembling all them together to form a code. This will be the final code. If you can see stage wise, enabling clocks, resetting GPIOs, programming GPIOs, programming resetting the pull up pull down, and then programming the pull up pull down, monitoring the flag, which is a part of which is taken from the IDR register, and monitoring the flag to actuate the peripherals. So if you observe here, I am performing AND with negation of 0x all this, because I don't want to disturb the state of remaining GPIOs. I want to only shut down this particular GPIO pin. And also if you observe here, I have used bool variable because I need only 1 bit data flag. Instead of using int, I can use a bool which will save memory. So this is all for coding point of view. Now let us see the simulation. Before moving into simulation, let me show you my Keil code. So this is a code that I have written in the Keil µVision. After writing it, you have to compile and then build. Once you are build the hex file, you can move to the Proteus, and there if you observe, I have connected LED to PA.0 and then switch to PA.1, and you can pick your hex file and place it in the program file provision provided here. After that, you can click on simulate. So now if you click on a switch, you can see that LED is glowing. So this is nothing but the process or flow that you have to follow for interfacing any input or output peripheral to a STM32 microcontroller. So thank you for watching. If you like my video, please share and subscribe to my channel and support me. Thank you.